Hello everyone, good afternoon. I'm Ziqing from CISPA, and I am presenting our work titled SecurityNet, Assessing Machine Learning Vulnerabilities on Public Models. Commonly, for research in machine learning security and privacy, the researchers would construct and train different models themselves to mimic the potential target for their proposed attacks or defenses. This allows the researchers to have full control and flexibility when producing their experiments. However, this approach also has its drawbacks, particularly on how realistic these models are. Models trained by researchers tend to have limited variation in architectures and datasets. As we all know, training large models on complex datasets is time and resource intensive. Furthermore, even with the same architecture and dataset, self-trained models often struggle with performance. Typically, you need to fine-tune hyperparameters to get the best results to compete with the state-of-the-art models. But security and privacy researchers, this process is often too time-consuming, leading to weaker models. It is kind of like food quality inspection. Each company might claim their food is high quality based on their own tests, but a standard is needed for a fair comparison. Thus, developing advanced attack and defense mechanisms is crucial, but it's just as important to ensure that experimental findings match real-world outcomes. So, how do we bridge this gap? Recently, the research and machine learning community has been increasingly focused on open source access and reproducibility. As a result, many pre-trained models are now publicly available on platforms like GitHub and Hugging Face. Many of these public models closely resemble those used in real-world applications, unlike those trained by security and privacy researchers. Consider the large amount of models available. The public models have a high variety of architectures and datasets used for training. Also, these models will tend to have better target task performance. For instance, many of the models are released to compete with state-of-the-art models on the specific dataset. The publisher of these models, subsequently, will ensure that they have as good of a performance as possible. Therefore, we believe using these public models can be a great starting point to bridge the gap between models used in current machine learning security and privacy research and those deployed in the real world. To support this, we introduce our SecurityNet database and use it to evaluate the performance of current attack and defense methods in more realistic scenarios. We focus on image classification models as a starting point, given their popularity in the security research community. After reviewing various platforms and repositories linked to papers from top machine learning, CV, and security venues, we found a total of 910 public models. This collection offers a wide variety of architectures and training datasets. We further annotate the relevant information of each model from 3 dimensions, namely model, dataset, and metadata. We hope this information can help security researchers find appropriate public models promptly. From all the models we collected, we categorize them into benchmark models and security models. Benchmark models typically come from collections like the official PyTorch library or from researchers releasing pre-trained variants of their new architectures through GitHub repository. Security models, on the other hand, are linked to trustworthy machine learning research, such as security, privacy, and safety. We distinguish these 2 types of models to compare and highlight the differences noted earlier. We find that, first of all, most security models are indeed trained on smaller datasets with simpler architectures, such as ResNet 18 on the CIFAR10 dataset. Additionally, target task performance varies widely. That is, the variation in target task performance of security models is also much larger than that of benchmark models. For example, while almost all benchmark models trained on CIFAR 100 achieves over 70% accuracy. Security models, however, ranges from 10% to 70%. Then, we conduct existing attacks on these collected models to establish a baseline for future researchers and gain insights across a wide variety of models. For the attack and defense methods considered, we choose popular topics from more representative results as shown below. However, since we are working with pre-trained models, we are limited in our ability to modify the target models directly. For example, backdoor attacks requires training, so they can't be evaluated in this context. Then I will introduce our findings in these attacks or defenses accordingly. The first attack we consider is model stealing attack. The attacker aims to obtain a similar or equivalent model to the target model. We use baseline methods that minimize the difference between the mimic model and the target model's posterior. Thus, a higher attack accuracy indicates a more success attack. We find that across multiple datasets, the attack performance decreases as the target task performance increases, which is a negative correlation. For more complex datasets, such as ImageNet 1000, the attack becomes generally ineffective on high-performing models. Some datasets, like Cube, also present much higher attack difficulty, as shown here. Now, we can further compare the difference between security and benchmark models. As mentioned previously, security models have higher variability in target task performance. We can further distinguish them into two distinct clusters based on their target task performance, as the orange and green dots shown here. Green dots are the high-performing models. We observe that high-performing security models behave similarly to benchmark models, which are the blue dots here, where the attack performance negatively correlates with the target task performance. And the lower performing models, however, surprisingly show the opposite correlation. This behavior difference highlights the importance of having high-performing models for attack evaluation. For the second membership inference attack, the attacker's goal is to indicate whether a data point is used in target model's training process. Thus, a higher AUC score indicates a more successful attack. Our findings varies. Our finding is correlated with the previous findings. That is, attack performance strongly correlates with overfitting level. To clarify, the overfitting level here refers to the gap between a model's performance on training and testing sets. The public models, however, generally have very low overfitting level because of their high overall performance. As a result, these attacks achieve limited success on such models. We also observe that difference between the high and low performing security models on membership inference attacks. We can see here models with high target performance can be more vulnerable to the attack even at similar overfitting level. As shown here, the AUC score of the green dots are higher than the orange ones at the same overfitting level. The third adversarial attack aims to add perturbations to images so that the model would misclassify the perturbed images. We use a simple white box FGSM attack to generate adversarial examples. So a higher accuracy drop implies a more successful attack. Similar to model stealing, we find that attack performance negatively correlated with the target performance. And we can observe that the attack becomes ineffective on high-performing models. Lastly, we evaluate backdoor detection on those public models. Note that we can't fully evaluate detection performance since all the pre-trained models we used are supposed to be benign. However, we can still assess various factors of the proposed detection methods, for example, evaluating their false positive rates on our selected dataset. Among the three methods we evaluated, we find that NeuroCleanse has significantly higher false positive rates compared to the other two. Additionally, its exponentially longer runtime makes it impractical for deployment on realistic models that are larger or trained with more complex datasets. In conclusion, our large-scale evaluation shows that attack and defense methods can behave differently on these public models. Notably, models with lower target performance exhibit drastically different behavior under attacks like model stealing and membership inference attack. While we acknowledge that not all experiments can be conducted on pre-trained models, we advocate future researchers to include at least some public models in their case studies for more representative results. We introduced our SecurityNet database to simplify the search for appropriate models. And we are maintaining this long-term project and are committed to make this database up to date. Thank you for your listening, and I'm happy to take your questions.